Let's solve Unit 9 Data Communication and Computer Networks questions. Consider the three-way handshaking process followed during TCP connection establishment between two hosts A and B. Let S and R be two random 32-bit starting sequence numbers chosen by A and B respectively. Suppose A sends a TCP segment having synchronization bit is equal to 1, sequence number is equal to S, and acknowledgement bit is equal to 0, and B accepts the connection request. Which one of the following choices represents the information present in the TCP segment header that is sent by B to A? The connection establishment in TCP is actually called as three-way handshaking process. So that is what they have mentioned in the very first line. They have given two hosts A and B. What is this SYN bit? This is actually to initiate connection establishment request. So when the bit is set, it means a request is initiated. Then we have acknowledgement number in the option here. This acknowledgement number is the sequence number of byte expected next. We also have another bit called FIN bit. This is actually to mention that the connection is terminating. So FIN bit is set while terminating the connection. Only at that time the bit value will be equal to 1. So from three of the bits here, SYN, ACK bit and FIN bit, what you can understand is all these three are Boolean values. It means they either have the value of 0 or 1. When they say this field is actually set, it means the value is equal to 1. Now they say A sends a segment having sync bit is equal to 1, sequence is equal to S and acknowledgement bit is equal to 0, and B accepts the connection request. So the scenario given in the question is what happens when A initiates a connection request to B. Now they have told B has accepted the request. What happens when B responds back to A? In this three-way handshaking process, we will see what will happen actually. The client sends the first segment. It has a SYN segment in which only the SYN flag is set. It means the value is equal to 1. This segment is for synchronization of sequence numbers. It consumes one sequence number. Here they have represented 32-bit sequence numbers as S and R. So A will have S and B will have R. When the data transfer starts, the sequence number is incremented by 1. You can find S plus 1 in 3 of the options. It means the sequence number is actually incrementing there. Now this is actually the scenario where A initiates some request to B. The next scenario is the server sends the second segment, a sync and acknowledgement segment with two flag bits set. The sync value is 1 and the acknowledgement value is also 1. Both the bits are set to 1. It is a SYN segment for communication in the other direction, that is from B to A, and serves as the acknowledgement for the SYN segment. So this is for communication in other direction, and this is the acknowledgement sent for the SYN segment that came from A. So this is SYN of A. For that purpose they are sending acknowledgement, and this also consumes one sequence number. What about the next part? The client sends the third segment. This is just an acknowledgement segment. It acknowledges the receipt of the second segment with the acknowledgement flag and acknowledgement number field. The sequence number is the same as the one in the SYN segment. The acknowledgement segment does not consume any sequence numbers. This is the next scenario. So in three-way handshaking, these three scenarios happen. So the first scenario is what is given in the question, as suppose A sends a TCP segment. And the second scenario is what they have asked us to find from the options. What will be present in the header when B communicates to A? Now we will just check. They say the SYN segment and ACK segment will be set to 1. So wherever you have both the values to be 1, those options can alone be kept now. SYN bit is equal to 1 and ACK bit is equal to 0. So we will rule out this. We have SYN bit as 0. So we will rule out this. We have SYN bit as 1 and ACK bit as 1. Here also SYN bit is 1 and ACK bit is 1. So we have to find from 3 and 4 only now. This is a SYN segment for communication in the other direction and serves as the acknowledgement for the SYN segment where this consumes one sequence number. A sends with the sequence number S to B, and this particular acknowledgement will just consume one sequence number, means this S will become S plus 1 when B is responding back to A. This serves as an acknowledgement for the SYN segment that is actually sent from A. So we have to increment this part here for the acknowledgement number. So where do you find the value S plus 1 here? Only in option 3, since it says it consumes one sequence number. So what does consuming sequence number means? We can say the sequence number is incremented by 1. In that way we can take this to be S plus 1. And what about the sequence number of B? It is R. So this sequence number is actually present here. This is B's sequence number and this is A sequence number that is incremented by 1. So we can even rule out option 4 because it is going to send acknowledgement number as S, the same as A, which is actually wrong. So in that case we can mark option 3 as the right answer. Now what about the FIN bit? It is set to 0. It means it is actually communicating. It is not terminating the connection. Then it has to terminate the connection. The bit will be set to 1. Only when you understand what happens in three-way handshaking process, you will be able to pick up the right choice here. Next question. Two computers A and B are configured as follows. A has IP address and a subnet mask. B has IP address and a subnet mask. What one of the following statement is true? So they are asking from the perspective of A and B what they assume, whether they are on the same network or whether they are on the different network. So how should the process be done? From the point of view for A's IP and A's subnet mask, both should be taken for bitwise AND operation. Similarly, B's IP and A's subnet mask again has to be taken for bitwise AND operation. This is with respect to A. The subnet mask of A will be manipulated for bitwise AND with A's IP as well as B's IP. The similar case will happen in case of B. So we will take the B's subnet mask in both the cases, and here A's IP will be manipulated and here B's IP will be manipulated. So this is what we are going to do now. The value of IP address is in decimal dotted notation. So we will just go with 2 power 0, 2 power 1, 2 power 2, 2 power 3, 2 power 4, 2 power 5, 2 power 6 and 2 power 7. When all the bits are set to 1, the value is actually 255. When all the bits are set to 0, the value is 0. So let's take the A's IP first. It is 203.197.2.53. and the subnet mask of A is 255.255.128.0. What will AND operation do? Whenever both the inputs are 1, the output will be 1. This is the case of AND operation. So when you do AND operation between 255 and 203, the result will be 203 again. 128 plus 64 is actually 192. 192 plus 8 is 200. 200 plus 3 is 203. So we will have 1, 1, 0, 0, 1, 0, 1, 1 in 203. So when you are going to do AND operation with 255, wherever you have 1 in 203, those places will again be 1 here, which will give you 203. So when you do AND operation with 255, the same number will be repeated. So in this case we can retain 203 as it is. What about 197 and 255? So when you are going to do AND operation with 255, again 197 will be retained. And just check for the 0 here. We have zeros everywhere when the value is 0. 1, 2, 3, 4, 5, 6, 7, 8. How do you do for 53? 32 plus 16 is 48. 48 plus 5 is 53. So we will have 0, 0, 32 plus 16, 0 here and 101 here. This is going to be 53 and this is 0. When you do AND operation, what you will get, irrespective of the ones in the 53 part, you will get zeros everywhere, because 0 with 0 or 1 will give you 0 only. That is AND operation. So in this case, when you manipulate anything with 0, the value will be staying as 0 only. We have to find only for 2 and 128. That we will do it now. So we will have dot 0 here. We have to write it for 2. So this bit is 1 and the rest of the bits will be 0. Actually this is for 2. And what about for 128? Only this bit will be 1. The remaining bits are 0 for 128. Now just do AND operation here. Everything will be 0 because 1 and 0 is going to give 0 here. 0 and 1 is going to give 0 here. The rest of the places are 0. When you get zeros everywhere, this is equal to 0. So the value of AND operation between A's IP and subnet mask will be 203.197.0. The final value is also 0 because when you do AND with 0, you will get 0 ultimately. Now we will check it with B's IP. The A's subnet mask will be staying the same. So when you do AND operation between 203 and 255, this will be retained. 255 and 197, this will be retained. Between 0 and 201, this will be retained. So I will even mark the places here so that you will know that. Now we have to find for 75 and 128. So what is 75? It is 64 plus 11. So 64, 72, 74 and 75. The remaining places will be 0 here. What about 128? Same thing, you have to have only 1 here. In this position, the remaining places will be 0. So why have I actually divided this into column is, in one of the previous question paper, I just wrote this in random and people were not able to see it properly. That's why this time I have just divided the columns for better clarity. Now we have to do AND operation between these two. 1 and 0 is 0, 1 and 0 is 0. This is also 0, 1 and 0 is 0. These two are 0, 1 and 0 is 0 and 1 and 0 is 0. So we are getting 0 everywhere. So the value will be 203, 197, 0 dot. The final value is also going to be 0. We got 203.197.0.0 in both the places. So this is from the perspective of A. Now we have to find from the perspective of B. So here we are taking the subnet mask of B. So this is the subnet mask of A. Now we have to manipulate it again. 255 and 203 will give you 203. 255 and 197 will give you 197. 0 and 53 will give you 0 only. Now we have to calculate for 2 and 92. So 2 in the sense only this bit will be 1. The remaining bits are marked as 0. What about 192? 128 and 64 together will make 192. So we are just making these two bits as 1. The remaining bits are 0. Now we have to perform AND operation here. No bits are actually same here. So this is 0, this is 0. This is also 0. So you have only 0 here. Now what will be the value? 203.197.0.0. Now let's do the same thing for B. B's IP with B's subnet mask. 255 and 203 will have 203. 255 and 197 will have 197. 0 and 201 will have 0. Now we will go for 75 and 192. 192 we know the first two bits are 1. The remaining bits are 0. What about 75, 64, 8, 2 and 1? The remaining places are 0. Now we have 0 and 1 as 0. We have one bit that is having 1 in both the places. This will give 1. This place has 0. This place has 0. This one is 0, 0, 0, 0. So what is this when you have 1 only here? It means it is 64. So AND operation between these two will give a value of 64. Now just write the value 203.197 dot, the third place will have 64 because we have one bit here in both the places, and the fourth part is 0 as it is. Now we will just take according to A, the AND operation between A's IP and A's subnet mask gives a value of 203.197.0.0, and from A's subnet mask we are computing AND operation with B's IP, we get the same value. So from the point of view, A thinks that both are on the same network because they have the same value here. So this concludes they are on same network. What about B? For B, A is in 203.197.0.0, but when it computed with B's IP and its own subnet mask, it ended up with 203.197.64.0. So from the perspective of B, both are on different networks. This is B's viewpoint and this is A's viewpoint. Now just read the options. A and B both assume they are on the same network. No. B assumes A is on the same network. B actually assumes that they are on different networks. So this part is actually wrong. So we can take this to be wrong. And the second part, A assumes B is on different network, is also wrong. What about C? A assumes B is on the same network. That is right. But B assumes A is on a different network. This is also right. So 3 applies perfectly here. Option 3 will be the right answer. For A, B is on same network, but for B, A is on a different network because of the different values we have found out from the bitwise AND operation. The fourth option says that A and B both assume they are on different network. This is also wrong. So when you are sure about 255 and any number X, the value will be X. 0 and any number Y, the value will be 0. These two things has to be in mind so that you can minimize the number of computations involved in finding the bitwise AND. So from the name we can take, we have to compute it bitwise. That's why we are finding the binary equivalent of the decimal dotted notation values that are given in the question. Next question. A class B network on the internet has a subnet mask of 255.255.248.0. What is the maximum number of hosts per subnet? We have solved such questions already in previous year question paper. The maximum number of hosts is given by the formula 2 power n minus 2. So let's take the decimal dotted notation and again we will go with finding the binary equivalent. So 255 means you will have 1 in every place. So you have 8 ones here. 1, 2, 3, 4, 5, 6, 7, 8. And for 248, 128 plus 64 is 192. 192 plus 32. It is 224. 24 plus 16. It is 240. 240 plus 8 is 248. And the remaining 3 places are 0 here. What about this 0? You will have 0 in all the 8 places. So this is the binary form of the decimal notation. Now what has to be taken as this power n? The number of zeros are to be counted for calculating total number of possible hosts per subnet. So when they say subnet mask has these many values, they will also use a notation called /21. It means 21 ones are present here. Just calculate. Here there are 8 ones, here there are 8 ones, and here there are 5 number of ones. Altogether 21 ones are present. It means how many zeros are present? 1, 2, 3. This is 1, 2, 3, 4, 5, 6, 7, 8. So there are 3 plus 8 which is equal to 11 zeros present. So here we can take the value of n is equal to 11. Let's find the maximum number of hosts. What is 2 power n? It is 2 power 11 minus 2. 2 power 11 can be written as 2 power 10 into 2 minus 2. 2 power 10 is 1024. This is 1024 into 2 minus 2. What is 1024 into 2? It is 2048 minus 2, which is equal to 2046. These many hosts will be there per subnet. Option number 3, 2046 will be the right answer. So they have given you the values of 1024 minus 1 and minus 2. Similarly, 2048 minus 1 and minus 2. So always keep in mind while calculating the number of hosts, we have to go with number of zeros. I hope you remember some learning already. The network ID will be actually 32 bits. If 21 bits are going to be for the subnet mask, if they are going to be 1, then definitely the remaining 11 bits will be equal to 0, which will give you the number of hosts per subnet. So when you add 21 and 11, it will give you 32 ultimately. Next question. In a token ring network, the transmission speed is 10 power 7 bits per second and the propagation speed is 200 meter per microsecond. The 1 bit delay in this network is equivalent to what? They are asking in terms of meter. So the delay in the network is equivalent to some distance or some length, we can say. Token ring network is a LAN that uses a ring topology and token passing access method. So what about the given values? They have given the delay as 1 bit in the question, and we have two other values, transmission speed and propagation speed. So what is this propagation speed? 200 meter per microsecond. In 1 microsecond, 200 meter distance can be covered. We will get into the calculation. This 1 bit delay can be taken as 1 bit into propagation speed divided by transmission speed. So 1 bit will stay as it is. Please have a follow of the units so that you should end up with meter at last. What is the propagation speed? It is actually 200 meter per microsecond divided by transmission speed is 10 to the power 7 bits per second. Now this 1 bit will stay as it is, into 200 meter also will stay as it is, and now this 10 power 7 can be written as 10 power 1 into 10 power 6 bits per second. Now we will bring this 10 power 6 to the numerator. This will be 1 bit into 200 meter per microsecond into 10 to the power minus 6 seconds. Then divided by 10 power 1, which is equal to 10. This bit is alone here. Per second has moved to the numerator along with 10 to the power 6. Only bits are there. This bit and this bit will get cancelled. So we have 200 meter per microsecond into, what is 10 to the power minus 6? It is 1 microsecond. So we will have microsecond here divided by 10. This microsecond will also get cancelled. Ultimately you will have 200 meter divided by 10. Cancel the 0. You will end up with the answer 20 meter. Option number 1 will be the right answer. Only when you keep the units meter per microsecond as it is, you can understand how that microsecond is getting cancelled from the denominator value. Next question. Consider a CSMA CD network that transmits data at the rate of 100 megabits per second over 1 kilometer cable with no repeater. If the minimum frame size required for this network is 1250 bytes, what is the signal speed? Kilometer per second is the unit in the cable. For collision to be detected, the frame size should be such that the transmission time of the frame should be greater than twice the propagation delay. Any possible collision will be discovered before the frame is completely sent. For that purpose, they are setting this particular condition. Transmission time is greater than twice the propagation delay. So I have included a equal to symbol here so that only by equating these two formula together we will be able to get the signal speed. So what are the formula for transmission time and propagation delay? Transmission time is equal to frame size divided by bandwidth. Propagation delay is equal to distance divided by speed. Now we will substitute these values in this particular place. Instead of transmission time, we are using frame size divided by bandwidth. Instead of propagation delay, we are using distance by speed. From this question, we will be able to get three values. The frame size is given as 1250 bytes. The bandwidth is actually given as 100 megabits per second and the distance is mentioned as 1 kilometer. So we have to find only this speed. Now we have to substitute those values. Frame size is 1250 bytes divided by 100 megabits per second greater than or equal to 2 into distance is actually 1 kilometer. We can retain the kilometer as it is because this unit is also in kilometer only. Divided by speed. So instead of speed I am just going to denote this by S. In the denominator we have megabits but here it is bytes. So what we will do, 1250 into 8. I am just converting them to bits divided by 100 into mega will be 10 to the power 6. So we know 10 to the power 3 is K and 10 to the power 6 is M. This is bits per second greater than or equal to 2 into 1 is actually 2 kilometer divided by S. So here we can cancel bits and bits. So I can write 1250 into 8 divided by, instead of 10 to the power 6, I can just change this as 10 to the power 5 and I will add 110 here making it to be 1000. So this is 100 into 10 to the power 1 which is actually 1000. So I am splitting 10 to the power 6 as 10 to the power 5 into 10 to the power 1 to make it to 1000 greater than or equal to 2 kilometer by S. So what is 8 divided by 1000? This is 8 ones are and this is 125. So 125 into 8 will give you 1000. So this is 125 and this is 1250. It means here you can have 1 and this is actually 10. So we have 10 into 1 which is equal to 10 divided by this per second is actually here. So we will retain the per second as it is. So this is 10 to the power 5 per second. So let's equate this because we have to find S. This is 2 kilometer divided by S. Now I'll bring S to the other side. So this will be S into 10 divided by 10 to the power 5 per second which is equal to 2 kilometer. So in order to find S, we have to bring this to this side. So this will become 2 kilometer into 10 to the power 5 per second divided by 10. 10 to the power 5 can be expressed as 10 to the power 4 into 10 to the power 1 divided by 10 and this is per second. This 10 and this 10 will get cancelled. So overall you will have 2 and 4 number of zeros. This kilometer per second will be retained as it is. So the value of S will be 20,000 kilometer per second. This will be the signal speed in the cable. Option number 4, 20,000 will be the right answer. So the kilometer per second unit is already given in the question. We have to just equate the value alone. Next question. Arrange the following steps in a proper sequence for the typical process of a DNS query. So just to solve this question, we will use a diagram now. So here we have the client or the web browser something, and first request is to a local DNS server. From there it is asking a root DNS server. From there it is asking a top level DNS server, and from there it is going to the authoritative DNS server, and from there you have replies marking 5, 6, 7 and back to the browser once again. So here you can find the local DNS server is having a DNS cache. So first it will check the cache and then it will go to the root for further querying. So let's start answering this. We have query authoritative DNS server, local DNS server check cache, root DNS server, and TLD DNS server. TLD is top level domain DNS server. So it has to start with the local DNS server. So the web browser or the client will be querying the local DNS server first. So what will happen when it queries the local DNS server? The DNS server will actually check the cache first. So BC. After checking the cache, if it does not resolve or if it does not find what it is needed, it will query the root DNS server, which is D. This root will query the top level DNS server, that is E. And this top level domain DNS server will go to the authoritative DNS server. So here D, E and A. B, C, D, E, A. Option number 4 will be the right answer. This is with respect to the scenario that is given in the question. You will have a local DNS server. If it cannot find it out from the cache, it will query the root DNS server. So the order goes like this. But in general scenario, instead of this local DNS server, we have something called recursive DNS server. This will act as a DNS resolver, we can say. So to whomever it wants to ask, this particular server will ask and fetch you the answer. The DNS recursor is a server designed to receive queries from client machines through applications such as web browser. So here we can equate it to local DNS server. The root server is the first step in translating or resolving human readable host names into IP address. This particular part. The top level domain server is the next step in the search of a specific IP address, and it hosts the last portion of a host name. This particular server. Then the authoritative name server is the last stop in the name server query. This one. If the name server has access to the requested record, it will return the IP address for the requested host name back to the DNS recursor that made the initial request. So here you can find the communication is between the DNS server and the root server, the DNS server and the top level domain server, the DNS server and the authoritative DNS server. This is what latest articles actually say, but if you get into DNS querying, this is actually the exact procedure that is quite close to the question that is asked. Next question, they have given you 5 statements and they have asked choose the correct answer from the options given below. So we will check the statements. In IPv4 addressing, a block of addresses can be defined as x.y.z.t/n, in which x.y.z.t defines one of the address and /n defines the mask. It is perfectly right. The first address in the block can be found by setting the rightmost 32 n bits to 0. This is also right. Address of class C is used for multicast communication. Here I have listed the classes and their application. If you take A, B and C, all are unicast. This multicast is for class D addresses and class E is for reserved purpose. So option C is actually wrong. Just rule out the options that have C, and this says option 2 will be the right answer for this question. The next statement, there are 5 classes in IPv4 address A, B, C, D, E. Yes, it is right. Supernetting combine several networks into one large network is also right. Next question, host A on TCP IPv4 networks send an IP datagram D to host B. So A is sending to B a datagram D. This is also on TCP IPv4 network. Assume that no error occurred during transmission of D when D reaches B. Which of the following header field may differ from that of original datagram D? This is actually A and this is actually B. If you are going to change the source and destination, the datagram will not know from where it started and where it has to go. So definitely D and E can never be different from the original datagram. So these two fields will stay as it is, because we have to know who sent the datagram and we have to know for whom is the datagram. So this will not change. Any options that involve D and E can be ruled out. Now the question is whether A and B are alone there or even C is there. So let's check the options individually. The time to live field is used to control the maximum number of hops visited by the datagram. When a source host sends the datagram, it stores a number in this field. This value is approximately twice the maximum number of routes between any two hosts. Each router that processes the datagram decrements this number by 1. So every time the value gets decreased during every hop, and when this number reaches 0, it understands that it need not be sent further. From this, what you can understand is TTL will change, because every router will decrement the number, means every time the number of hops will get reduced. So imagine there are 10 routers in between. When you reach the 7th or the 8th router, the number will be 1 or 2 only. So for every router, this value will be changing. So TTL is in. The header field may differ from the original datagram is the question. So TTL will definitely differ. And we know TTL is a part of the header now. When one field changes, automatically the checksum value will also change. The checksum in the packet covers only the header and not the data. When I say one of the value in the header is actually changing when we visit every router, it means the checksum has to be computed every time. It means checksum is also different from that of the original datagram. So this field is also changeable only. So A and B are definitely there. The only question that comes here is whether C is included or not. I'll just tell you a scenario here. The original datagram, we'll just imagine it has 4000 bytes. The numbers are from 0 to 3999. We know there are many routers in between A and B. Take for example, this is R1, this is R2. We know that every router will have certain capacity to send. If this datagram is going to be greater than the capacity of a particular router, automatically fragmentation will occur. As per this example given in the screen, the router has a capacity of only 1400 bytes, but the datagram is of 4000 bytes. So it has to send 1400. This is first fragment. This is second fragment, and the third fragment will be 4000 minus 2800 will give 1200. It will be split this way: 1400, 1400 and 1200. So if you add up all these, you will get 4000 totally. So the maximum capacity of a particular router is going to be 1400, means this 4000 packet will be fragmented into 3. So the first fragment carries bytes 0 to 1399. The second fragment carries bytes 1400 to 2799. And the third fragment, the final one, it carries 2800 to 3999. So for every fragment, see the offset calculation here. You have 0 here, you have 175 and you have 350. I am not getting into the calculation of offset, but here the story is, when the datagram size is going to be large than the router's capacity, the datagram can be fragmented. They have not mentioned anything about the don't fragment field and all. So if the don't fragment field is set to S, you have to not fragment it, you have to find another route. You have no other go. But if that field is not set, it means the datagram can be fragmented. If the datagram is fragmented, definitely this fragment offset will have different numbers. When the original datagram reaches B, this field may not be same when we take this into account. Keeping this case in mind, we can mark fragment offset also as the answer. So we can go with option number 2, A, B and C only. Next question, match list 1 with list 2. They have given IP address in list 1 and they have asked to match it with the respective class. We'll just have an idea. So A is from 0 to 127, B is from 128 to 191, C is from 192 to 223, D is from 224 to 239 and E is from 240 to 255. 10.20.30.40 is lying in the range of A. A will be mapping to 3, class A. A3 is available only in option number 4. Then we have 210.20. 210 means it is in the range of C. So B is mapping to 4, class C. What about 180.30? It is in the range of B. C will be mapping to 2. 252.5. This is in the range of E obviously. So D will be mapping to 1. Option number 4 will be the right answer. When they say it is 0 to 127, only this particular number is taken for range. So the from field will have 0.0.0 and the to field will have 255.255.255 definitely. Next question. Match list 1 with list 2. This is about the layers. So we'll just see a diagram here. We are seeing the physical layer, data link layer, network layer, transport layer and application layer. We have the involvement of bits in physical layer. So A representation of bits will be mapping to 2. A2 is available only in one option. Then they have given about segmentation and reassembly. So this part, segments, can be taken as a clue. So D will be mapping to 1, transport layer. What about the address? So when it is network layer, we go with logical address. When it deals with data link layer, we can term this as physical address. Old edition books will refer it as physical address and new edition book will refer it as link layer addresses. We can map B physical address to 4 data link layer and C logical address to 3 network layer. It is directly available. So if it is physical layer, it is bits. If it is data link layer, it is frame. If it is network layer, we can say it is a datagram or packet. When it is transport layer, we can again use the word datagram or even segment. So messages are involved in application layer. Do have an idea about the particular packet names of layers as well as the address terms used there. With this, we are completing Unit 9 solutions.